Hello, I'm Chris Mack, your professor for the class from Data to Decisions. This is Lecture 43 on comparing models. In particular, what if we have two models and we want to know which one is doing a better job of fitting the data? If the number of parameters in the model is different between these two models, well, then that comparison is a little bit complicated. So let's talk about it. First of all, to remind you, in building a model, we often strive for parsimony. That is, we want the simplest model that does a good job. You can always make a model more complicated. You can always add more and more and more terms to the model. But it's kind of a waste. It's wasted effort, makes the model more complicated, more difficult to interpret, more difficult to use, more difficult to calibrate data if you have unnecessary terms. But sometimes a simple model is not good enough, right? So we add more predictor variables, we add more complex functions of the predictor variables, we add interaction terms, so that model can become, with just a few different variables, it can get extremely complicated. And then you start adding 5 or 10 different predictor variables, and the number of possible combinations is tremendous. When you add these terms, extra predictor variables, complex functions, interaction terms, how do you know that when you build this model, you're actually doing something useful with these terms? How do you know you're not just fitting the noise, something we call overfitting? Well, we could use R² to tell us how good the model is, and that's fine if you're comparing two models with the same number of adjustable parameters. But R² always gets better when you add more model terms. So I can't use R² to compare a model with fewer terms to a model with more terms. Let's go back and review what R² is, the coefficient of determination. It's a measure of how much of the variation in Y has been explained by your model. When you make the model more complicated, you always make R² bigger. Recall that we've defined the sum of the squares of the errors, the difference between the data and the model itself. That's the sum of the residual squared, sometimes called the residual sum of squared. Unfortunately, that sometimes gets confused with the regression sum of squares, which is, of course, a different sum. And the total sum of squares on the bottom is a function of the data only. It's not a function of the model at all. So R² is something like 1 minus the residual sum of squares divided by the total sum of squares. These things are all related for a linear regression, although this equation is not true for nonlinear regression. So every time I add a new term to my model, I by default always make the residual sum of squares less. It has to be less. It could possibly be the same, but in general, it's always going to be at least a little bit less every time I add a new term to the model. So SSTO is a constant, therefore R² is always getting bigger as I add more model terms. One way to fix this problem is to adjust the coefficient of determination. We call it the adjusted R² or the adjusted coefficient of determination. And we do that by adjusting the sum of squares errors and the sum of square total by their degrees of freedom. So if I have P model parameters that I allow to adjust to get the best fit, and instead of saying R² as 1 minus the sum of squares of the errors divided by the total sum of squares, I'll instead say it's equal to the mean square errors divided by the mean square total. In other words, variances, or my estimates of the variances, taking the sum of square errors divided by the number of degrees of freedom. Now I have a sort of a penalty for adding more parameters. I might make the sum of square errors less, but that doesn't necessarily mean I'm going to make the mean square error less. You can do a little bit of algebra, rearrange the equation, the definition of the adjusted R², and you find that the adjusted R² is always less than R² whenever P is bigger than 1. So if I have 2 or more parameters in my model, I will reduce the adjusted R². By how much? Well, 1 minus r squared is the unexplained variance. That unexplained variance is weighted by p minus 1 over n minus p. So the more parameters I have, the larger this term gets. Of course, that's balanced by how better r squared gets and how much smaller the unexplained variances is. If I add new terms to the model, I might still make the adjusted r squared go down. That probably means I have a better model. But if I add a new model term, the adjusted r squared goes up. That's an indication that you haven't really made an improvement. And that term is probably not needed. So here's our first way of helping to compare models with different numbers of parameters. The other way we'll do it, and really a better way, is something called the information criteria. Generically, an information criteria is minus 2 times the log of the maximized likelihood plus some term that penalizes our model for being overly complex. All right, let's parse this a little bit. First of all, L is called the likelihood. We've talked about this before. We often use maximum likelihood methods to establish what the best fit parameters are. And L is the probability that I will get this data set given the set of parameters that I have. We adjust the parameters to maximize that likelihood. Regression software very commonly calculates this and can return this quantity after doing a regression. The best fit maximized value of the likelihood. Then, of course, if we know what L is from the regression, we can take the log of it and multiply by 2 very easily. And then we need to add a complexity term. The goal then is to balance the improved likelihood by adding more model parameters to the worsening complexity when we add those model parameters. So every time you add a model parameter, maximized likelihood is going to go up and minus 2 log likelihood is going to go down. But our complexity term is going to increase every time I add a parameter. So the idea is to find the right balance, and we want to find the model that produces the smallest information criterion value. This is generically how they work. Let me give you 2 examples. But first, let's look at this likelihood again for the case of IID normal errors. Ordinary least squares regression assumes that all of the errors are independent and identically distributed and that they all have a normal distribution. Because they're independent, I can multiply all the probabilities together. Every probability is a Gaussian, so they all have the same sigma epsilon error distribution standard deviation. And therefore, when I multiply all the probabilities together, I get this expression where chi-square, as we've seen it so many times before. Now, if I take minus 2 times the log of that likelihood, my expression simplifies like this. Now you can probably see where the minus 2 came from, right? If I take the log of the likelihood and it's this Gaussian function, I'm going to get this minus 1/2 out in front. So if I multiply by minus 2, it kind of cancels that out. So minus 2 times the log of the likelihood just simplifies the math a little bit. And I get chi-square plus n times the log of 2 pi sigma e squared. Sigma e squared is the variance, the true variance of my residuals. Okay, so that's what minus 2 log likelihood is. But remember that if all the assumptions of my ordinary least square regression are true, we know the expectation value of chi-square, because chi-square will be chi-square distributed. So the expectation value will be n minus p, where p is the number of parameters in the model. Therefore, the expected value for minus 2 times the log likelihood is shown here, n minus p plus this n log term as well. What happens when I add more parameters to the model? Well, first of all, get a straight minus p phenomena, but also adding more parameters to the model should make the variance of the residuals get smaller. Now, that's the log likelihood piece. Let's look at the added complexity piece. At what I think is the most popular information criterion, Akaike information criterion, or the AIC. The AIC is minus 2 log times the log of the likelihood, and the complexity term is simply 2 times p. Well, you can sort of see where that came from by going back a moment to the previous slide. We saw that the expectation value of the chi-squared is n minus p. So one of the p's simply cancels out this minus p term here. And then the second p is probably the simplest complexity penalty you can have. You simply linearly add an extra number for every time you add an extra parameter. So we're just adding a p, and that complexity term then means I have to balance extra parameters p with improved log likelihood, in particular the improved log of the variance of the residuals. Now, log likelihoods are computed in regressions up to an additive constant. So here is an example of a log likelihood that you might get back from a specific regression piece of software. You can see where it came from the previous expression. The sum of square errors divided by n, that's our estimate for the variance of the residuals. We also have this n log 2 pi n term. I have a weighted regression, then I include this. If I don't have a weighted regression, all the weights are 1. Log of 1 is always 0, so this goes away. But when I compare two log likelihoods to each other, when I compare two AICs to each other, these additive constants don't matter. The fact that I add n or I add n times log of 2 pi, it doesn't make any difference. The thing that's going to matter is the sum of square errors going down compared to 2p going up when I add more parameters. So if you ask one piece of software to calculate the AIC for you, and you ask a different piece of software to calculate the AIC for you, you're likely to get two different numbers. That's okay, because those two different numbers differ by only a constant for a given n. And there's still a difference between the AIC when I compare one model to another model will be the same. And that's how we're going to use these information criteria. I'll compare two models, the same data set, but two models with different keys or different parameters. And I want to know which model is better. The additive constant won't really matter. Now, there's another information criterion called Schwarz's Bayesian criterion, or Bayesian information criterion. We'll see both of those terms used, and it uses a different complexity term. Instead of 2 times p, it uses p times log of n. Well, is that bigger? Is this complexity term penalizing my criterion more? Well, it depends on the value of n. If n is 8 or larger, then the natural log of n will be bigger than 2. And for that reason, BIC penalizes you more for a more complex model that has a larger value of p, as long as n is 8 or more, which is almost always going to be the case. So let's summarize. If we want to compare models with different numbers of parameters, we have to be careful what kind of goodness of fit measure we use. We need a goodness of fit measure that will penalize our model for getting too complex, for getting too many parameters. So we have these three modes of measuring the goodness of fit: the adjusted R-squared, the AIC, and the BIC. what are the differences between using one or the other. If I want to find the best model, either maximize the adjusted R-squared, or I want to minimize the AIC or the BIC. Well, if I use the adjusted R-square, this results in models that have larger number of parameters. The BIC penalizes us the most for having more parameters, so it results in a model with the smaller number of parameters that it says is the best model. In other words, the most parsimonious model. The AIC is somewhere in between, and in my experience, that's the more popular choice for most people, and it gives you kind of a compromise between these two extremes. I tend to like parsimony, so I either use the AIC or the BIC when trying to decide. But what I generally do is calculate all three every time. Sometimes they all agree. All say this is the best model. When that happens, then of course you don't have to worry about it too much. When they disagree, then you have to decide whether you want to emphasize parsimony or not. And there's no right answer. There's no way of saying this is a better model, because it depends on what you mean by better. All right, let's review what we have done. As always, you should be able to quickly and easily answer each of these questions. Why can't R-squared be used to compare models with different numbers of parameters? Explain the adjusted R-squared and how it is used. What is an information criterion and how is it used? And finally, the use of which information criterion of the two that we've talked about results in the most parsimonious model? Well, that's it for this lecture. In the next lecture, we're actually going to use R to calculate some of these metrics and compare models. Till then.